a quick recap from last time. Last time we have seen state space, the state space representation for a system. And we have seen that a state space representation has this form. There is this variable x that is the state of the system, is chosen as the state of the system, and it's going to be a function f of potentially the time, the state itself at time t, and the input u, so it doesn't involve any output. The output instead is going to be given by a function that we call h of t, x, and u. Of course, there is going to be, we didn't consider that the other time, but we considered that in the examples because it was important. There is also an initial condition. So we have one first equation that is gives us the state dynamics. The other equation gives it's the output equation. If we know the state, the time, and the input, we know the output, and then we also have the initial condition. This is a possible way of defining a dynamic system. The other possibility is an input-output relation. The input-output relation is going to be given by a function g that involves the output, the first derivative of the output, we are going to call it dt y, and so on, derivative of the output up to a certain order that we call ky, dt ky, and also the input, the first derivative of the input maybe, and as many derivatives as we want up to a ku derivative. So this function here, g, has to be equal to 0 and defines an implicit relation between the input u and the state y. As an important thing, the state, the output y. I was already thinking about the next thing I wanted to say, that no state is needed here. So this seems to be a more economic way of representing our dynamic system, assuming that these two representations are equivalent because they describe the same relationship between the input and the output, namely that if you give me a certain input, you can infer the output in the same output from both representations. No state is needed in the input-output relation. Okay, so these are two different ways of representing a system, and in one of the next lectures we are going to see how they are related to each other. So far we are simply considering that a system is given either in one form or the other, and we are going to analyze the system given the specific representation that is given to us. That's what we have done, and we have also considered some examples in which, in these examples, it was not as important to know the input because there was actually no input. The systems were isolated, and so it was really not that important to make a distinction between these representations, and we could assume that we were using a state representation because it didn't make a lot of sense to consider an input-output relationship because after all there was no input. However, what we considered two examples. We considered the Malthus model that was given by, let's say, an equation like this, that was leading to, we were considering also the initial condition x0, was giving us something of this kind, exponential of at x0 for its dynamics, and Malthus with, we call it with competition, it's typically called with logistic, but with competition, let's keep it calling like this. And it was nothing but a generalization of the previous model, where we had this additional term that is called logistic term. And this leads to a more complicated expression for x of t that look like this. It was 1 divided by b divided by a minus, and then we had again b divided by a minus 1 divided by x0 for exponential of minus at. So this was the expression, the expression that we got, and we verified that when b goes to 0, actually this matches the expression that we were seeing, that we had here. Okay, what we are going to do today is going to be mostly an introduction to Matlab and Simulink, and we are going to at least to simulate at least these two models, and we are going to verify that these equations are actually correct. So in order to do this, we start our Matlab. Here I have already started it because the computer I'm using is quite slow, so it takes some time to start a software that is as heavy as Matlab is. So I assume that most of you are familiar with Matlab. I'm just going to introduce you to the commands that we need for the specific exercise, that is to simulate in a numerical way instead of deriving in an analytical and mathematical way as we have done the other time. What we are going to do is simply to simulate numerically these two models and verify that the equations that we have derived are actually correct. So the first thing that we do is to enter the directory where we want to work. So we are going to do that. And in order to enter your directory, you use the command cd. Doesn't matter which operating system you're using, you're always using cd, at least inside Matlab. And I should have already a directory here called Matlab files. If you want to list all the files that you have in this directory, you use the command list, ls. Again, inside Matlab this works, I assume, no matter what your operating system is. And after verifying that we have nothing there, so this directory is completely empty, we can start creating files, scripts, and so on. Otherwise, another option is just to work inside the command window, and all the variables that we are going to create here are going to appear in our workspace. The workspace is this panel that you see here on the side. So let's start mentioning some basic things about Matlab. An important feature about Matlab is that in Matlab pretty much every variable is a matrix, and this makes very easy to do computations with matrices, multiplication with matrices, to compute eigenvalues from matrices, and so on. So most variables pretty much tend to be treated as matrices. In order to define a matrix, if you want to define a matrix A, you use the square brackets and you start populating it with whatever you want. In this case, I have just generated a 3 by 3 matrix. If you want, you can compute the determinant of the matrix A, and in this case is going to be around 0. Matlab computes everything numerically, so don't expect to find an exact 0, even though if you compute the determinant of this matrix A, you're going to find exactly 0. Matlab finds a very, very small number. So since the determinant of A is 0, means that the rank of A is not going to be 3. It can be anything between 0, 1, and 2, given the information that we have. In particular, I know that the rank of this matrix A is 2 because it has 2 linearly independent columns. I assume that all these things from linear algebra are already familiar to you, so these are very standard things that you can do in Matlab. If you want to just clean up your command window without erasing, deleting any of the variables that you have in your workspace, we can see them here on the right hand side, you just use CLC, and as you can see, your variables here on the right hand side stay there. If you really want to reset your workspace, you simply go with clear, and all the variables that you have defined are going to be deleted. Now, how do we start Simulink? Simulink is a part of Matlab, is a toolbox in Matlab, or an addition to Matlab, that allows you to simulate systems as the ones that we see in our class. And it started by simply typing Simulink, or maybe there is something that you can do in the GUI to start Simulink. I'm pretty sure that you can. However, if you start Simulink like this, at least in this version of Matlab, you have the option of starting with a blank model, a blank subsystem, or you can create a library and so on. Simulink can be extended with your own libraries. Well, what we are going to do is something very simple. We are just starting with a blank model. So while the model is being created, we wait, and here we have it. The model being created is just a blank screen where nothing is in there, and now we need to populate it with what is needed for our simulation. We are going to see how to simulate things if we are under the assumption that we're using a state space representation, at least for today. And maybe in other classes we'll switch to an input-output representation so that I can show you how it is done in the other way. But what we are going to do today is very simple. Let's go back to our equations. Let's start with our Maltose model. So we want to implement these equations here, x dot equal to ax, and also we need to somehow provide Matlab with the initial condition for the simulation. What we do is this. We open what's called the library browser. Here we have the library browser is just a collection of blocks that are ready, they're ready made for you to use right away. And when you want to build a model using a state space representation, I'm giving you this sort of recipe. The first thing that you grab is from the continuous blocks. You drag and drop on your model an integrator. Now, here the dimension, the size of this integrator is pretty small, so let me make this a little bigger for you so that we can actually see things better. So this is the integrator. This block acts in this way. You insert an input and the output is going to be its integral. The fact that it's represented by 1 by s depends on, we haven't seen the Laplace transform yet. An integrator using the Laplace transform is represented symbolically as 1 divided by s, where s is a frequency variable. We'll see this later. So far, I just want you to know that whatever the input is, and we are going to put a certain input signal here, the output is going to be the integral of that signal, at least the numerical integral of that signal. So what we are going to do is, in Matlab we can also do this. If you double click, you can create an annotation. So the annotation that I'm going to write here is, I'm saying that my x is the output of my integrator. So I put my annotation close to the output of this block, and now I have this this annotation here that is just to remind me that I want the output of this integrator to be x. So if the output of this integrator is x, let's go back to our equations. If I have as an input of my integrator the derivative of x, I have created the relationship x dot equal to something. So what I want to do is to put as an input here the derivative, input to my integrator, the derivative with respect to time of x, that my equation tells me is going to be a times x. So I'm going to grab some blocks from my Simulink browser to create the expression a times x. The expression a times x is just obtained by taking x and multiplying that by a scalar quantity a. So what I'm going to do, I go into the math operation subfolder. I grab this variable here that is called gain. A gain is nothing but a multiplication by a scalar. I drag and drop it here. I have my gain. Now if I use Ctrl R as a shortcut, I can actually rotate my gain. And I'm waiting for this to be rotated. And now what I do here, I click inside the gain and a window opens up and asks me, what is your gain parameter? I want to use a generic parameter a, and now Matlab is going to protest a bit, saying that a is not defined, but if we define that in the command window, we are going to be fine. So far I'm just leaving it open. So I have a, and Matlab is warning me with this red flag that a is not defined yet. But at the moment I don't care, and I simply connect my x into the gain. So the output of this gain is going to be a times x. If I check my equation, a times x is the derivative of x. So if I connect this here, I have written in the Simulink language the expression x dot is equal to ax. So this represents my Maltose model. Now I have to add something to this block. The block by itself is actually it would actually work with only one thing. We haven't put the initial condition yet, and we are going to do it in a second. But first, I'd like to tell you that you need to add some other things so that you can visualize the variables, the outcome of your simulation. In order to do that, again, we need to go back to our library and go at least in the sync part. And from the sync part, there is a block that is called workspace, and I drag it here. So in this block here, I'm going to define a variable. I'm calling it x. What this block here now does the following thing. Let me rearrange things a little better. But if I put this here, the block is a sync, so it takes only an input, and it's just to manage variables with a configuration like this. Now, when I run my simulation, the x is the values of x of my simulation are sent to the workspace in this variable out.x. So it's a way for Matlab. There is a variable out, and this variable is a structure, and x is going to be one of the fields of this structure. I don't like actually to use structures, so we change this to just being a standard array. So what we can do to do that is the following. We can press, we can actually see in the simulation. Now I need to, let me make this a little bigger. Let me see if I can find in the model settings. I go into model settings that can be called using Ctrl E, and now I have this interface that is going to be ready for me in a second. Okay, here the interface is a little complicated. I'm just telling you the basic things that you need to modify. For example, if you want to make a simulation longer, The simulation here starts from time t equal to 0 and goes up to time t equal to 10. That for what we want to do, I think is going to be enough, but if you want to make it longer, you can replace the stop time with something, with a bigger value. Then you're going to have a solver selection. There are two options, either variable step or fixed step. I said there are two options, but actually there are only one option. Always go for variable step. That's the way to go. In terms of solvers, you can go with the automatic selection, that's fine, but otherwise there are many algorithms and you can actually choose the algorithm that you prefer. What is typically chosen as a default most of the times is the ODE, ordinary differential equation algorithm, for 5. 4 and 5 have a meaning. They tell you something about the precision of the algorithm. We are actually keeping the automatic selection. And now a most important thing, please pay attention to this. I don't know why, but Simulink has, in terms of relative tolerance for the algorithm, a default value that is too high. So we have to have a relative tolerance that is much smaller for any kind of real application. Even for the simulations that we do in class, this value of 1 divided by 1000 is not going to be, it's really not a good choice for this, but it's the default value. So what I recommend is to have at least 1 divided by 1 million as relative tolerance, or even smaller. So this is the relative tolerance that we have. So this has to be changed. Please always change it every time you use Matlab. Of course, changing this makes running your simulation slower, but considering what we are going to simulate, this is not going to be a problem. So, and otherwise, it's not, if you have a simulation that runs fast but is not accurate, I still can argue that you're not simulating things properly. So we do this. Another thing that I forgot, sorry, I'm pressing again Ctrl E so that the same interface appears again. Another thing that is important, at least to me, is the data import export. As I mentioned before, I don't like to have things that are in a structure or something that is too complicated. Maybe I'm a little old school, but I just want an array. I just want vectors in my workspace. So I like this, and I also like to. We'll see what I mean. I don't need all these things. I choose what variables I want in my workspace manually. Again, might be an old school thing, but I deselect everything. You can keep these things, just choose the format array if you're doing things the way I'm doing them now, and you can also have other variables exported to your workspace. I'm okay if I do everything manually. Since I'm doing everything manually, I need also the time, because I want to plot my x versus time, so I need to export the time. So to export the time, I do the following. I need another workspace block that I drag here. So as you can see, because I've changed the format of the variables from structured or data to just a simple array, this is not called out.x anymore, it's just simply called x. I'm going to call the variable that I use for time t, and here I have it. And let's check in the way this variable is saved. Again, choose array in the type of variable. We are going to do this again for the time. Double click on the workspace and say save format as array. This is how I do things. If you like time series and how Matlab handles time series, you can go that way. I'm simply old school. I only deal with arrays. What is the input of the time? We go in the Simulink browser, and as a source we take this block here that is a clock. So we take our clock and we connect it by clicking on the clock and dragging the arrow into t. Here we are going to have, once we simulate our system, we are going to have two variables in our workspace. One is t, and it is a list of times, and the other is x, that is a list of values of x. If we plot t and x, if we put t and x in the same plot, we have our numerical solutions plotted for us. Only one thing, and then we'll be able to go. We need to specify the initial condition. To specify the initial condition, you specify that in the integrator. In the integrator, the initial condition is going to be by default 0. I'm putting x0, and again Matlab is going to warn me that this x0 variable is actually not defined. So as you can see, these blocks have red flags, both of them. So the way to run our simulation is then to define in the workspace a value for x0. I define 1, and I need to define also a value for the parameter a, and I'm going to choose 1 for this as well. As you can see, in my workspace I have my variables that are defined. If I go here, I don't know why it's still complaining, but everything should run just fine. To start your simulation, you simply go, I go with a shortcut. It is Ctrl T. With Ctrl T, you start your simulation, and now you hear this beep sound, means that the simulation has finished. We go back into our workspace, and now we can see these two variables, these two new variables, t and x. T and x are populated with some numbers, and if we plot t and x, we're going to see that this is an exponential curve, and it starts from 1. We can actually verify that it starts from 1. Just by magnifying it. Just 1 second. It seems that Matlab has made it difficult in this interface to magnify things, but believe me, if everything has been done correctly, you're going to be pretty much guaranteed that the initial condition is should be equal to 1, because I'm not exactly at time 0, so forgive me for this. Well, one thing that we can do is, it used to be, I don't know where the magnifying glass is, maybe here. Let's see if I can do this in a better way. So if I choose the magnifying glass, just by zooming here, I should be able to grab it. Yeah, as you can see, the initial condition is exactly 1, as expected. Okay, so this was just a warm-up. The Maltose model is pretty much the simplest model that you can imagine. So let's close our plot. Let's go here. Let's just clean the common space. All the variables are still here, and what we are going to do is to modify this. So the first thing that I'm going to do is I'm going to save this model in my folder, and I'm going to call this Malthus, and now it is saved like this. Of course, the parameters a and x0 are not going to be saved. They are in the workspace. We are just saving the structure of this model. So I'm going to give this model to you, and I'm going to post it on Canvas. When you run this, remember you have to initialize the parameter a and the initial condition x0 so that this model is going to work. Now we are going to modify this in such a way that we get our our expression ax minus bx squared, and then we'll verify that this is the expression that the analytical expression that we got is the same as the numerical expression that we received, or at least very close to it. Okay, so what we have here is that x dot is not equal to x, at least not only. We need to have ax minus bx squared. So the idea is to go again into the math operations, grab another gain. This gain is going to be b. So I'm calling this gain b. We are grabbing again x. We are making a bit of a mess. So now we have b, and as you can notice, b has not been defined yet. And now we need to sum a and b squared. Sorry, first I have to square x before putting that into b. So I go again in my math operations, and I need to look for a square. So there is a math function here that is that we can use for that. But today I feel like using a product. So the product is different from the gain, because the gain is a multiplication of the input by a scalar that is fully specified by the gain. The dot product instead is the dot product of the two inputs. If one input is x and the other input is x, you can use the product to do the square. And then you use the scalar gain to have b squared. And now we need to sum ax and b squared. So what we do, we go into the math operations, and there is a sum block. The sum block has this nice round shape, and it can be modified. If you give a list of signs, you can have an algebraic sum, so you can sum or subtract. In this case I have decided to give it this shape, and I subtract minus bx squared, and I add a. The initial condition is still x0, so this model here that I have just modified, I'm going to save it. So I'm going to save it. I want to save it as with another name. So let's see if I can find the way to save it with a different name. I'm used to a completely different interface, so this Matlab is too new for someone old like me. But let's see if I can, because if I press Ctrl S, I'm simply going to overwrite what I have saved before. So let's see if I can do, where is the save as? Okay, so far I give up. So what I'm going to do is the following thing. I'm going to do this. I'm going into my operating system. I'm going to take this and I save it back with a Malthus old, and I'm going to save this again. So now this Malthus with logistic is the new Malthus, and the Malthus old is the Malthus without logistic, without competition. And then I'll give you appropriate names when I post this on campus. Okay, we have this. We just need to give a value to b. So the value that I'm going to give to b is just 1 to try things. And here I'm going to press Ctrl T so that I can start my simulation. And well, actually I don't like b equal to 1. I'm going to choose b equal to 2. And I'm going to simulate this, and the simulation is done. Actually, one little trick, it's just eye candy. In the sinks there is also this display. I can do this, and I can display the time here. So let me redo the simulation again. As you can see, now it was so quick, but once the time becomes 10, the simulation is done. And we go into our workspace. Now we have again t and x, and we can plot t and x. So now, as we can see, we see that we start from 1, and the population decreases and goes towards 1/2. And the reason being is that the population is going to converge towards a value that is given by the ratio between A and B. So if I change the value of B, and instead of making it 2, I make it 0.1, we'll see that if we rerun the simulation again, the population is going to increase from the initial value of 1 up to 10. That's at least what I expect. And that's what we expect. Exactly what we expected. So as you can see now, I can change the parameters and apply and run my simulation in any way I want. The other thing that I want to do, and then we can be done with this illustration, is to take this expression here and simply verify that what we have as a result of our simulation matches what we have computed here. So what I'm going to do is I'm just writing my x theoretical, and I need to write an expression for x that is going to be exactly this expression. So the expression is going to be 1 divided, and now I'll need to modify this in 1 second, but 1 divided b divided by a minus parenthesis, and I have b divided by a minus my initial condition, that is x0, but it needs to be the inverse of the initial condition, and this quantity here needs to be multiplied by the exponential of a times t. My variable t is defined here. So this is not going to work, it's going to give me an error for the following reason. Matlab treats everything as a vector, so let's see. When I'm computing the exponential of at, t is a vector that, according to the workspace, has 52 points. So the exponential, so a times t, a is a scalar. A scalar can multiply a vector. You get a vector of the same dimension. So a times t is totally fine. When you take the exponential of a vector, it gives you a vector with all the exponentials. That's how Matlab interprets this expression here. Then and so it's still a vector. Then you have this quantity here, b divided by a minus 1 divided by x0. It's a scalar. A scalar can multiply a vector. So this expression here gives absolutely no problems. Then you have a scalar minus a vector that in math we cannot do it. Matlab instead is smart enough. If you have a scalar quantity minus a vector, it makes this scalar quantity a vector of the same dimension of the vector. And so what you obtain is that you get a new vector such that every entry is b divided by a minus the correspective entry of this vector. So this is still fine. The problem is when you take 1 and you divide a scalar by a vector. This Matlab doesn't like this kind of operation. You need to specify that you want an operation done entry by entry. So you want the inverse of each entry of a vector, and the vector in question is this. So you want the inverse of each entry here. So to specify, to tell Matlab that this is the inverse of each entry, you write, instead of the standard division, the entry by entry division, the entry-wise division that is represented in Matlab by this expression. So if we do this, we find our values for x theoretical, and I made a mistake. I needed to put a minus a here, so let me repeat the computation. Here it is. So this is the expression that I have just entered, and these are the results. Now, when you start having very long vectors, it's annoying to have them displayed, so you can avoid displaying them by just using, by ending everything with just a semicolon. So what we have now in x theoretical, we have this expression here. So what we have is our plot with what we have computed numerically. What we do is hold on. Hold on means that we are going to plot all the next plots without deleting the previous plot. Otherwise Matlab deletes the previous plot and just keeps the new one. Hold on says no, keep all the plots always there, and we are going to plot, instead of x, we are going to plot x theoretical. And to make a distinction, we are going to plot this in red with diamonds. So it's not going to be a continuous line, we are just going to see red diamonds there. As you can see, the red curve was our theoretical expectation. It is exact. What we are verifying, it's not that our expression is actually exact, because it's derived theoretically. What we are checking in reality is that our simulation is correct. But sometimes you derive a theoretical expression, you are not sure that you made no mistakes, and so it's good to verify. You might trust a simulation more than your own calculation sometimes. So it depends on the degree of certainty that you have on the two items that you are verifying. However, we can be reasonably sure that both the simulation and our theoretical derivation are correct because they virtually match exactly. So this is just a simple introduction to Simulink, so that we have seen how to simulate simple systems. So far we haven't seen how to introduce inputs there, but introducing inputs is actually going to be quite trivial, and we are going to do that in the next class, where we are going to use Simulink.